right, so the next test we're going to talk about is the ratio test. The ratio test works well when there's lots of different things. Like there is exponentials and factorials and polynomials, all those things. So for the ratio test, what we're going to look for is we're going to look at any two terms, consecutive terms, an plus 1 and an. So an is our normal term, an plus 1 will be the next term, and we're going to look at the ratio of the limit of those guys. So basically it's kind of like a geometric ratio, is that we're looking for this to be less than 1 as n goes to infinity, and then it will converge. If it's bigger than 1, it will diverge. And if it's equal to 1, the test fails. And it's usually because you should have used an LCT, limit comparison test. Okay, so looking at this first one, if I tried, like right now we know this is harmonic, p equals 1, diverges. We know that. But if we tried to do the limit, the ratio test, so the first thing we would do is we'd go through and we'd say an is 1 over n. an plus 1 is 1 over n plus 1. Then you do an plus 1 over an, and you see that limit is equal to 1, which means that's inconclusive. We should have gotten that divergent right away. If we did the same thing here, and we did an and an plus 1, we'd still get the limit is equal to 1 and divergent. It will work for anything that should have been done on LCT. If you try to do ratio test, it fails. Okay, so when I use ratio test is normally when there's lots of different things that are moving around. Ooh, didn't mean to go that sideways. That was crazy. So here we have lots of stuff. We have a polynomial piece. We have a geometric piece. Now, I would love to say that this converges. I can just look at that and know that. And eventually you will get better at it. But right now that's not a safe assumption because we know this grows because it's on the top, but this one is going to 0. So we don't know which one's growing faster. Okay. So what we do is we go through it and do the ratio test. So an is exactly what's here. An plus 1, all we do is plug in n plus 1 everywhere you see an n. And then you're going to do the ratio of these two. So when you do the ratio, you're going to multiply by the reciprocal. And then we always look for things to cancel. So here we have a geometric 3 to the n plus 2. Down here, 3 into the n plus 1. So we have one more on the top. We have one more 5 on the bottom. Then if you look at that, the only thing left besides this 3/5 are n plus 1 squared and n squared, and we're going to infinity. So we're looking at the n behavior, which is the ratio of the leading coefficients. You see, that's what we had left. So that is 3/5, which is less than 1, so this converges. And again, number 4, probably the same type of thing going on here. We know that this grows, and this grows also, and this grows faster, so we expect this to go to 0. But again, it's not a proof. So the proof is the ratio test. So first thing we do is find an, and then an plus 1, and you do the ratio. The absolute values don't mean anything right now, so you multiply by the reciprocal. Then we can see that our geometric pieces cancel, and then our polynomial pieces with that factorial leaves us with n plus 1. The degrees are not equal, so the limit is 0, which is less than 1, so it converges. Same thing here. We have this. An is 2n plus 1 2n factorial. An plus 1, let's make that very clear real quick. This would be 2 times n plus 1 factorial, which turns it into 2n plus 2 factorial. Remember, the rule is you replace n with n plus 1. So you can see here that our degrees are not equal. Here we have degree 5, but these guys we have a 2 more, so it's going to be greater than 0. In fact, it's going to be infinity, so it diverges. Ratio test. Same thing here. ratio test. Again, canceling the geometric, then canceling any factorials. Then you pay attention if the degrees are equal or not, and then it's the ratio of leading coefficients. Same thing, an plus 1 multiplied by the reciprocal of an. The degrees are not equal after you cancel everything, so diverges. Now the rest of them are kind of AP problems that have showed up in the past. They want to know what values of x this converges. Well, if this converges, I need this to be less than 1. That's just the ratio test. So we have those values. Same thing here. We want to know for what values of p. So I think all values of p it's going to converge because the degrees will be equal. I should write that. Here we have this one converges. You see the factorial on the bottom, factorial on the top diverges. This one, we move it down to the bottom, and then it's going to converge. Going through the ratio test here. And again, whenever it tells you ratio test. So you go through and just cancel everything, and you see what happens. For the ratio test to converge, you need to be less than 1. Right here, an plus 1 over an is 6. So we want to know which one will converge. Well, an wouldn't because we know that that ratio is 6, which is bigger than 1. So if I try this one, I would get an plus 1 over an plus 1 because that would be your nth term. So my nth term for this one right here would be an over n to the 7th, and the an plus 1 term would be an plus 1 over n plus 1 to the 7th. You can see right here the degrees are equal, and then this value is equal to 6, so therefore it also diverges. Here, slightly different, we have a geometric on the bottom, and right here, this now, if this is equal to 6, and then we have 1/7 to the n, that will definitely converge. Ratio test inconclusive. It's inconclusive whenever it should have been a LCT, a limit comparison test. So it's going to be inconclusive here and here, but not here because the degrees will be equal. Diverge compared to 1 over n. Diverge factorial on top. Diverge nth term test. And then here's just a little matchy-matchy to see that you have the conditions on the test matched correctly.